left channel, right channel, center.
VTuber 一問一答自己紹介
Yeah, and the tape's
それじゃあ
rolling.
行くよせーのお名前は
Katt Phloxworthy.
呼び方は
Just Cat is fine.
あなたは何系 VTuber?
Nerdy cat girl who features spaceflight.
誕生日は
May 4th.
年齢は
Older than Pneumatic.
性別は
Transgender
身
female.
長は
4'11".
出身は
Sacramento County.
チャームポイントは
Dialogue hair clip.
突然ですがモノマネどうぞ
Yeah, what's up, Dad?
活動場所は
Twitch, Twitter, YouTube.
はじめの挨拶
Thank you for joining me.
終わりの挨拶
Bye.
推しマークは
Not at present.
配信タグは
Catlight feed.
ファンアートは
Cat pics.
ファンネームは
Cat's apprentices.
好きな色は
Iris Indigo.
好きなことは
Vintage computers and
得
video.
意なことは
Technology.
ここで一言愛の告白
I love you.
好きな食べ物は
Ethnic foods.
好きな飲み物は
Craft soda.
好きな漫画は
Pizza 10.
好きなアニメは
Planet.
好きなゲームは
Left 4 Dead 2.
好きな音楽は
Classic rock.
苦手なことは
Human stupidity.
尊敬するのは
Space fairy people.
叶えたい夢は
ISS crew
最後にみん
interview.
なに一言どう
Thanks
ぞ
so much for your support and a final status check.
Go Atlas.
Go Centaur.
Go Katt Phlox.
You have permission to launch.
3, 2, 1. RD-180 ignition. Booster ignition and liftoff of Atlas V and Centaur. Hello, everybody, and thank you so much for joining me. Hi, Katt Phloxworthy here. My first Rocket Lab launch in quite a while, especially since a lot of the stuff happens during the times I'm at work, and on top of that, the reason why, and it's also the first time since mid-April. So, anyway, we will be heading there a bit later than normal. They apparently pushed the launch back by about 18 minutes. Don't know what the exact issue is going on, but they're saying that this was as of about let's see, let me see if there's any information in here. They're saying this was as of about almost 55 minutes ago. They're in the process of loading propellants onto the rocket. It says, I'm just doing a just taking a quick look of the latest stuff up there. They're see what's happening here. They are so basically they're running about 18 minutes behind as far as the actual launch time. No specific explanation on that, but of course we can understand that there might be things going on such as last minute changes, last minute adjustments, and we'll be picking up Rocket Lab in just a bit. But anyway, this one is called Symphony in the Stars. Basically, there's going to be a don't know why it's called that, but apparently there's a launch of a satellite that's going up tonight. But apparently there's like one of two launches supposed to happen. I'm not sure if the other one has happened or has happened already or has yet to happen. We may or may not necessarily get to see what's going on with that. Well, at least we could see at least the first two portions of the actual launch, first and then second stages. The rocket that we're using tonight, that they're going to be doing tonight, is the Rocket Lab's Electron rocket, which is their first product. The next one, there's another one in work right now. The Electron is a two. It looks like two stages, but it's usually three. Basically, what happens is they launch off. The first two first get it off the ground, and the other gets it into orbit, and the third is to get it where it needs to be in orbit. The first stage is just the first two are just like regular first and second stages. The first stage is to get it off the ground, powered by 9 engines running a mixture of liquid oxygen rather, and RP1, which is a highly refined form of kerosene. Actually, both the first and second stages run that. The first stage goes up to what is called MECO, which is just about a minute and a half after the launch, at which point the second stage separates and then ignites the second stage, which is a single engine, which takes it up to orbital velocity, which is about 17,000 miles an hour, or about 17,500 miles an hour, or 27,000 kilometers per hour. And they'll use a much smaller engine on the third stage, which they call the kick stage, which is used to adjust the altitude in this particular case, as just to put it into a precise spot to drop it off in orbit. And then, of course, they will start operations. Don't know if there's any specifics about that. According to the site, according over to Rocket Lab, they're saying that it's the people who are putting that actually had the satellite. They haven't said anything specific about it. We're just going to watch the launch of the satellite itself. So, and thus far, they're saying everything is going to plan. Thus far, they've tanked all stages at this point. And this is the Rutherford, which is an electrode-fed rocket. Normally, you would see something like, for example, the Merlin 1D, which is a gas generator-fed engine, which uses a turbopump in the open cycle configuration, where basically they run essentially another rocket engine to run that rocket engine. Basically, it runs what is called a turbopump, and the turbopump is what actually brings RP1 and liquid oxygen, which are roughly the same densities, and that allows them to use one common shaft to pump both stages with one gas generator. In the case of the Rocket Lab Electron, they use an electric-fed pump. Basically, they use an engine that runs off batteries, and in fact, we're going to talk about that a little bit later, right around during the second stage. They will actually I'd say 2/3 to 3/4 of the burn. They will actually drop off 2 external batteries, one of which we will actually see. The actual drop will happen within our sight, and there's a third within the actual vehicle's fuselage, and that one will take over after the other 2 detach. Actually, they'll start then detach, more accurately. So, and apparently there was a launch a couple of days ago. So this was a very quick turnaround between one rocket launching 2 days ago, and another one launching in I'd say roughly about 18 minutes from now. No, excuse me. It's going to be 23 minutes from now. My apologies. So basically, actually it is 18 minutes. My apologies. No, it is. Hang on. No, it is 23. My apologies. I'm not mathing well tonight, and on top of that, I just woke up from a nap earlier, so. And of course, I'm not sure if any of you saw what happened. I believe to one of the most recent Super Heavy. They were doing a static test and caught some of the folks from NASA spaceflight by surprise as they were covering it. They were just having idle chit chat, and next thing you know, boom! The thing just blows up on the pad. So, well, anyway, we'll see how long things will be until the next launch. They may have multiple first stages ready to go in case they need to, or ahead of additional launches. We'll have to see what happens, especially given the fact that it just outright blew up completely without any kind of warning. So, and of course, that's kind of important that everything works as it should, because people could be riding those rockets. Yeah, but in any event, I'm going to go check and see how things are looking thus far. Yep. Oh, I see. I was just looking at it earlier. I was reloading one of the status pages, and it hasn't changed much yet since I started the stream. So hopefully before too long, we'll be... Let me go take a look at something real quick, and we should be hearing... We'll be joining them before too long. But basically... what'll happen is right around 8 minutes after the top of this hour, they will they're shooting for launch. They will launch the vehicle, and plus about a minute and a half, they will, like I said, they will shut down the first engine, the first stage, drop the first stage, ignite the second, which will usually run from about another 6 minutes. And after the first 6 minutes, oh, okay, we're going to go ahead and join them right now. In fact, here we go. And there's still a problem with, and I tested that earlier, and I don't know why that's giving me trouble. So let me go ahead and get that moved off. Hang on a sec here. I just have to, I have to use the right computer to do that with first. Okay. They just started, and they'll be joining us before too long. So usually, this is a very small rocket. It's about 60 feet in height, and I believe it's like 2 or 3 feet in diameter, if that. Well, actually, it's probably going to be like closer to a full meter. I'm sorry, but anyway, if you look at the if you ever looked at pictures of Peter Beck, the CEO of Rocket Lab, sometimes he'll actually hold a Rutherford engine, a sea level Rutherford engine. Without all the connections to plumbing and all that other stuff and electricity plugged into it. It's about the size of a kitchen garbage kitchen garbage bag. Kitchen garbage kitchen garbage can. Excuse me. Yeah, I'm still feeling the effects of it, if you get my point. But anyway, it's really, really small. There's like, and since there's like 9 of those engines around the first stage, it won't play all that big. It'll probably be maybe about 2 meters at most in diameter. So that's about 6 feet in diameter or so. And then, like I said, the entire stack stands about 60 feet tall. And because I guess it's so small, and when you with that much with all that delta V going through it, especially when you light the second stage after separation, that thing just heads away real quick, and like Falcon 9 and Falcon Heavy, the latter when it actually is, it can be they can reuse the second stage, but they generally tend to expend those stages. But we'll see what happens before too long. So hopefully we'll be seeing some of the stuff that they're going to be talking about, and within the next roughly 3 minutes or 2 to 3 minutes or so. And what happens is that we may not necessarily get to see the upper stage, which of course is what they call the kick stage, with a very small engine which uses a monopropellant, I believe, of some sort of hydrazine, using some sort of catalyst, such as say platinum, basically acting as a catalyst to aid in the decomposition of the fuel, instead of actually burning the fuel. And usually what they'll show on the when it comes to the excuse me, let me try that again. When they the way those engines work is I believe they use a mesh of something like platinum, much like how, say for example, a catalytic converter works on a car, and they pass the fuel through that, and it makes the hydrazine decompose much more quickly. Basically, a catalyst speeds up or slows down a chemical reaction without actually being itself consumed. That's how catalysts work. And I saw a rather interesting demonstration of how catalysis works. Basically, you take the active substances within a catalytic converter, and they just put gasoline vapor on it, and what it does is it glows really hot. That's because it's actually okay. They burn it a lot. They burn it very hot. They burn it a lot quicker and without any kind of flames. There's the erecting of one of the rockets to the vertical position, and both stages are made of a carbon composite, and that is actually not paint there. That white on there, that is actually frost, because there is no insulation for the second, for either the first or the second stage. There's your kick stage right there. Let's see what they have to say. Also need to take a look at a couple
Good
things.
evening. You are looking at the moon as we have our Electron rocket ready on the launch pad at Launch Complex 1 in New Zealand as we prepare to launch our 68th Electron to space and second mission in less than 48 hours. It is T-minus 14 minutes 16 seconds in the countdown to launch for Symphony in the Stars, a commercial mission headed to low Earth orbit with a single satellite on board. And my name is Muriel Baker. It is good to be with you.
And I'm Kim Thompson. It's great to be here with another Electron launch,
And
this
Neutron
time from
is the
Pad
name
B
of their
at
new
our launch site. We are aiming for the first available opportunity within tonight's launch window at 7:08 p.m. local time or 07:08 UTC. Operations have been progressing smoothly throughout the day, and the weather has been cooperating nicely so far throughout the count and is expected to remain clear at T0.
Now, tonight, Electron is headed to a 650-kilometre low Earth orbit at a 96-degree inclination with the first of two satellites that we're flying this year
96 degrees,
across
it is
two
a
dedicated
retrograde,
missions for the satellite
orbit,
operator that is on board.
which is basically
It's also
about
said
6
to
degrees,
be part of our fastest launch turnaround yet from
facing
LC1.
away,
We were here
from
just
the direction
yesterday
of
on the
Earth,
next pad
Earth's
over
motion,
with the Get
rotation.
the Hawk Out of Here
Normally
mission
we would be
that
doing what
launched
is
at
posigrade
5:28 a.m. yesterday.
launching, basically
Now counting down to launch
launching in the
tonight,
same direction
set
as
for
the spin of Earth.
7:08 p.m. local time. We are just 13 minutes away from launching this back-to-back mission. And that means we are closing in on the go, no-go poll set to be run by tonight's launch director, Julia Wembacher.
We've got operators on console in 2 locations, our Range Control Centre on the Mahia Peninsula at the launch site and our Mission Control Centre here in Auckland. Tonight's mission is being led, as Muriel said, by our launch director Julia Wimbacher from MCC, and she's about to check in with each operator on their readiness for launch. From the stage operator monitoring the tanks and structures, avionics watching over Electron's electronic systems, to the range safety monitoring the range at LC1, it is integral for each team member to advise their final status. Let's hand it over to Julia and the team in Mission and Range Control and listen in.
See what we got. I think they're getting ready to do the go-no-go poll, which is at T-minus 12 minutes and counting.
And
or 11 minutes.
LD
no, it's 12
mission
minutes.
code. We are proceeding now with the go-no-go sequence. Stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
Recon.
Recon is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
LD sub.
LD sub is go.
The go-no-go sequence is complete. We are currently T-minus 11 minutes and 17 seconds in counting. We are go for terminal count auto sequence at T-minus 10 minutes. From this time, the 3-word procedure is in effect.
Well, that is exactly what we want to hear. Greens across the board from the launch operations team there. That poll confirms we are go for launch. Now, we have a 2-hour window of opportunity tonight, so if there is a hold for any reason in the remaining 10 minutes to launch, we have almost 2 hours to reset the clock.
Otherwise, time now to take you through our launch vehicle on the pad for tonight's mission. Electron is launching on a south-southwest trajectory from LC1 at a 96-degree inclination. And the rocket on your screen is our small lift carbon composite orbital launch vehicle capable of carrying up to 320 kilograms of payload. Electron stands at 18 meters or 59 feet tall and is made of carbon fiber reinforced polymer, otherwise known as carbon composite. And we use this material throughout the vehicle's first stage, second stage, and fairing, as well as for the rocket's internal tanks and its payload platform, the kick stage, that's found within that nose cone.
Well, powering this rocket, we have 2 types of propulsion systems across Electron. Staying at the top of the rocket, it's our Curie propulsion system, which powers Electron's kick stage once we're in space. We designed it specifically to provide the kick stage with precise orbital insertion and maneuvering capabilities for the payloads it carries, so that when we can reach each mission's desired orbit with high accuracy. The kick stage's operation is fully autonomous through its guidance and navigation system, which means Curie can start up and shut down even while out of sight of global ground stations.
Now, the engine behind our main propulsion system across Electron's first and second stages is the Rutherford. We've got 9 of these on the bottom of the first stage and a 10th vacuum version with an expanded nozzle that is optimized for space on the second stage. Now, all versions of Rutherford run an electric pump-fed cycle that is controlled by batteries, and the engine uses liquid oxygen and kerosene for its propellant.
And that white is, like I said,
yes, and it's that liquid oxygen, which is the reason why Electron has white stripes as it fuels up on the launch pad. It's where the propellant's super cold temperature causes moisture on the outside of the rocket to freeze. It's also a good level measure visually to know whether Electron's propellant tanks are full and ready for launch, which, judging by what we're looking at here and where the clock is in the countdown, tells us we're in the final moments of launch preparations
on the first
before
stage,
liftoff.
below that is the actual RP1, which is the fuel. But like I was saying,
LD stage.
Please proceed with sequence 58, stage terminal checks.
Copy, sequence 58 and work.
so they went into terminal count at T-minus 10 minutes. They had the minute before they had already called everything was go for launch. Actually, excuse me, was T-minus 12 minutes.
Please proceed with sequence 59, launch pad ready.
Copy and work.
All pump.
Tonight's back-to-back launch will be our 10th Electron mission this year, the majority of which have been for satellite operators that are deploying the next generation of constellations to low Earth orbit. And we've been ramping up Electron's launch cadence to meet the demand for regular, reliable and dedicated access to space that lets those constellation operators launch when and to where exactly it is that they need to place their next satellite.
Here's why and how Electron has become the go-to for constellation deployment across multiple missions.
So this is where Electron really comes into its own, as we're able to take the spacecraft and the customer and build their constellation spacecraft by spacecraft and put them exactly where they need to be for the longest lifetime and the most effective economics. There's two ways to get to orbit. One way is through a rideshare where you agglomerate a bunch of spacecraft onto one rocket, and the other way is to go and do it in a dedicated fashion, more like Electron, where you put a singular spacecraft on the top of the rocket and you get it exactly to where you want to go. Now, the one thing that we've seen over time is that rideshare missions have proved really, really important for initial customers to go there and put one spacecraft on orbit and kind of get a proof of concept. And then after that, we find more often than not, they'll come to Rocket Lab and request a bulk buy of Electron launches in order to deploy their constellation. And what that means is that they're able to accurately place each one of those spacecraft exactly where they need to be to build that constellation in the most commercial manner possible.
You can think about it as kind of like an Uber service. So we'll customize our missions to suit the customer's needs. We launch when they need and to exactly where they need to go to. Any special requirements that they have, we'll even engineer new processes to make that happen. We've created new guidance algorithms to be able to launch some of our upcoming missions.
Yeah, I mean, we have a saying within Rocket Lab is once you fly Electron, you never go back. And that's proven to be true. Customers come to us because we have just such great control over the accuracy of the position of the spacecraft and great control over the timing. We can put the spacecraft exactly where it needs to be, exactly when it needs to be. So customers can build their constellations quickly with us and also very accurately.
If they're wanting to build up a constellation from scratch, a lot of customers have an orbital plane requirement. So we'd target a right ascension of the ascending node or longitude of the ascending node. So for any satellite or sets of satellites, we can get the spacing between them exactly how the customer wants.
Well, people care about dedicated because time is money. And deploying the constellation to exactly where it needs to be, over the area where the density of population or the density of services is super important.
5 minutes and
I think a lot of people think just space is space, but it absolutely is not. Every satellite has like a postcode, if you will. Every satellite has a place that it is ideally suited to be to provide the best service to everybody.
You can imagine that would be talking within kilometres, tens of kilometres when we're talking accuracy. When customers come with us, usually they request on apogee and perigee plus minus 15 kilometres and on inclination plus minus 0.15 degrees. What Electron usually achieves is actually within a couple of kilometres on the apogee and perigee, and on the inclination we're accurate to usually the second decimal place. Our best to date was for flight 50. On the apogee we were 8 metres, the perigee 3 metres, and the inclination was plus minus 0 degrees.
That's pretty darn good accuracy. And apogee is the furthest point from Earth.
We're looking forward to launching more satellites for more constellation customers as the year progresses.
Otherwise, a check-in on the clock, and we are now at T-minus 3 minutes, 49 seconds and counting to launch with Electron. So in just a few moments, the countdown will be covered by the rocket's onboard flight computer from T-minus 2 minutes. And then final checks are completed autonomously by Electron as it prepares for liftoff, though it will continue to receive liquid oxygen into its propellant tanks up until about T-minus 1 minute and 30 seconds. We'll know that's been completed when we hear a call out from the mission control operator that the lock system is in recirculation.
After that, we should hear the call out that the rocket's first and second stages are fully pressurized for launch. And this happens around 30 seconds or so after LOX loading is complete. Then it's over to the 10-second countdown by our launch director, with Electron's Rutherford engines on the first stage set to ignite at T-minus 3
minutes
seconds.
and counting.
It's time to bring up the mission control audio channels now to hear our operators' call-outs live as they happen. So we'll be back with you after liftoff.
Lock the auto sequence and confirm.
Locked.
NVCon, please confirm all flight computer ESCOs are green.
All ESCOs are green.
To all operators, we are go for auto sequence start at T-minus 2 minutes. LDs go for launch.
So when the vehicle, so right around T-minus 2 minutes, the computers aboard Electron will take over the remainder of the countdown, monitoring the vehicles and the payload's health just prior to ignition. I've actually seen one where they actually aborted the actual ignition for launch at the time. T-minus 2 minutes and counting. Actually, they'd actually started, but they actually shut the engine
Vehicle
down.
is fully on internal power.
Now we're on.
FPS is green and enabled for flight.
Everything is now. The onboard computers are now in complete control of the rest of the countdown, monitoring the vehicle's health just prior to liftoff. T-minus 1 minute 30 seconds.
Is complete. System is in recirculation.
They've now terminated the load of liquid oxygen, and they're not going to be. They won't be adding any more oxygen. Ordinarily, they'd be topping up the tank to make sure everything is full on the liquid oxygen stage. T-minus 1 minute and counting.
Anti-geysering is disabled.
Looks like they're going for
Stage
a full
1 and Stage 2
launch
tanks are pressed for flight.
They just pressurized all the propellant tanks ahead of ignition.
High flow engine purge enabled.
T-minus 30 seconds and counting. Hey, Bryn, how you doing? 20?
T-minus 20 seconds and counting.
15. 10. 9. 8. 7. 6. 5. 4. 3. 2. 1. Engine start and liftoff of Electron carrying the Symphony into the stars. Mission to low Earth orbit, and the vehicle has cleared the tower. The vehicle is pitching down range, placing it above water in the event of an abort scenario. And there we see the Mahia Peninsula, which is at the southern end of New Zealand, dropping away in the distance. Coming up will be the next event, which will be Mach 1, or extending the speed of sound. And after that,
There goes our Electron rocket with a clean liftoff from LC1, now on its way to space for the 68th time. And we are steadily climbing in speed and altitude as Electron comes up to max Q, or maximum aerodynamic pressure. It's one of the first milestones the rocket has to pass through to get to low Earth orbit, and we're standing by for it now.
Mach 1.
Approaching max Q.
They will go through max Q, or maximum aerodynamic pressure, or the largest amount of atmospheric pressure the vehicle will experience as it goes down to goes through the lowermost portions of the atmosphere.
All right, we're clear through max Q there as Electron continues onto space, and everything is looking nominal across the rocket's speed and altitude. Now that we're past max Q, the next milestones coming up are main engine cutoff on the booster and stage separation. So very soon we can expect to see all 9 Rutherford engines on the first stage power down and shut off in preparation for what comes next.
Just a couple of seconds after Miko, the first and second stages will separate to lose the dead weight of the first stage. And then the second stage Rutherford engine will ignite and power up to propel the second stage onward to orbit. And those events
and then we're seeing views from the first stage itself. Those are Those are the flames coming from the first stage of all 9 Rutherford sea level engines.
Stage 1 propulsion holding nominal. Stand by for MECO in approximately 30 seconds.
So the next milestone is MECO, or main engine cutoff, shortly after which will be the separation of the first and second stages, then ignition of the second stage. Always fun to watch. Coming up on MECO.
MECO confirmed.
We have MECO. We now have a separation of first and second stage. Oh, I like the sound. My first time hearing that. The second stage is ignited, and that squarish thing that you see just below to the right on the engine is one of the 2 batteries that flank the engine on the second stage.
And a beautiful and clean second stage engine startup for Electron, nice and bright on your screen there. Electron's altitude is
That's
now
the
more
first
than
time
100
I've actually
kilometers
heard
an
the
hour.
sound
Coming
of
quickly
that.
to the command line.
Oh, we
as
actually are going to get to see some of this stuff. That's the payload itself.
Speed dial.
Everything is going great so far with Electron. With MECO and stage
now
separation
it's mainly going
cleared,
up rather
next
than
will be when Electron's nose cone
sideways
separates
rather
and
than
falls
up.
away. We might not see it at night, but we should hear it called out in mission control, so let's listen in.
We'll see the there goes the fairing halves.
Fairing jettison confirmed.
The fairing is
Nicely
2 halves.
done. That's fairing
2 conical
separation
halves
confirmed
that
across the nets as Electron
protect the vehicle
continues on nominally.
protect the
We are
payload
now
rather as
at
it goes through the
130 kilometers
as
in
it
altitude and
ascends from
traveling
the ground
more
all
than
the way up to about
9,000
100
kilometers an hour.
kilometers above the
All is on
surface of the
track with the
planet
mission,
or
with
the
another
Kármán
5 or so
line.
minutes to go of engine burn time for the second stage.
And right now they're shooting for right around 27,000 kilometers per hour, which is a nominal orbital velocity. And a little bit later, they will be jettisoning the 2 batteries that flank the engine.
Guidance is looking good so far with the second stage. The plot lines for our planned and actual trajectory are closely matched on the right-hand side of your screen there, which is exactly what we want to see. And now that we are at T plus 4 minutes, 36 seconds into stage 2 flight, we have got just over 4.5 minutes left of engine burn time before we reach SECO and stage separation.
Roughly about 2/3 or 3/4 of the way you'll see, of the burn. You'll see that and the battery on the other side be jettisoned because they have spent their supply of electricity in those batteries.
Well, coming up next for the second stage will be battery hot swap for that Rutherford engine. So every one of these engines uses an electric pump-fed cycle for its propulsion, with batteries used to power its electric motor. But the length of the engine burn time on stage 2 means that the battery pack it starts with will run dry before the engine is due for shutdown. So, Electron performs a maneuver called the battery hot swap, and that swaps in a fresh pack of batteries to keep the engine running for full duration. When that happens, you should see the first set of battery packs eject from the second stage and fall away. So let's watch out for that now.
Since it actually uses the batteries, the battery to spin the pumps, when the battery is expended, they actually have to drop the batteries because the battery is still basically dead weight right now. And they're coming up on the battery hot swap and jettison events before very long.
Nominal, approaching hot swap in roughly 30 seconds.
And those should disappear. That is one of the best pictures I've seen of the batteries thus far.
Throttling down.
They're throttling down in preparation of the battery hot swap and jettison of the spent batteries. Standing by. There go the batteries. They just got hot swapped. And now they're operating from a battery inside the fuselage.
On the second stage, the Rutherford is continuing to power the mission on past 198 kilometers in altitude at speeds of more than 1,600 kilometers an hour, coming up close to the
actually closer to 16,000
for final stage separation in just a few minutes.
And the first and their initial parking orbit will be elliptical with a high apogee and a low perigee.
Well, that glowing nozzle you can see on your screen is our Stage 2 engine, our vacuum optimized Rutherford engine, powering Electron and its payload, now past 201 kilometers in altitude and 19,000 kilometers an hour.
In the final event of this particular part of the rocket, they will be doing what is called SECO, second engine cutoff, which is the shutdown of the vacuum optimized Rutherford engine on the second stage. And the first stage, I'm not sure if they're going to do engine burns at first. They will use that initially to start altering the altitude.
Okay, we are just moments away from the final stage separation between Stage 2 and Electron's kick stage, preceded, of course, by the shutdown of the Rutherford engine for SECO, or second engine cutoff. The Rutherford engine on the second stage will throttle down before shutting off completely to allow for clean separation of the stages.
From there, the kick stage will enter a coasting phase around the Earth before we light it up for payload deployment within the hour. But first, let's listen in for that SECO and stage separation call out from Mission Control.
Coming up on SECO and third stage separation, which is the combination of the kick stage and the payload itself.
SECO confirmed.
Ooh, wow, we actually have sound of that. They have SECO.
Stage separation confirmed.
And that is SECO confirmed by Mission Control, along with the kick stage also confirmed to have separated
from the second
into a nominal transfer orbit with its payload. Well done to everyone involved in the mission so far.
Well, from here, we have a bit of a wait until we rejoin the kick stage and its satellite on the opposite side of the planet after its elliptical coast of Earth. Once that happens, the kick stage should be in the prime position to perform a course correction burn that sets its trajectory to a circular orbit for payload deployment.
Join us again then in about 40 minutes or so to see out the final moments of the mission. See you soon.
Basically, what they're doing right now, is waiting for the vehicle to wait to the other until it gets to the other side of the planet, which puts it at its highest point, the apogee of the orbit. At which point they will ignite that Curie engine, which is that tiny engine which has nowhere near the amount of power that's on the first or second stages. That engine there will be mainly, looks like they're not going to be changing the orbit, actually, in this case. Sounds like they're going to just use it to circularize the orbit, basically where it's the same altitude on every point of the orbit. In fact, that's what happens when crewed vehicles fly. They usually fly in what is called a suborbital trajectory. Basically, if they don't make any course corrections, they will actually fall back into the atmosphere. Like in case there's a problem, basically it's a quick and free ride home without having to worry about having to make any kind of course corrections in case something goes wrong. I'm going to turn that down just a little bit. But yeah, that's the first time I've actually seen them actually use, because I remember seeing the original, that one video that had, where they used a 360 camera to show the staging event, where from the lower stages, when MECO happens on the first stage, then they separate the second stage and then ignite the second stage, and the first stage just floats away and goes down and burns up in the atmosphere. And a lot of the staging events usually happen just below the Kármán line. But that's right around the time where they do they jettison the fairing. When they do a 5-meter fairing launch with the Atlas Centaur, they do that. They actually leave the fairing on. They jettison the fairing before staging, because for the 5-meter fairings, it actually encapsulates not just the payload, but also the entire second stage as well. If they use a 4-meter fairing, they only encapsulate the payload instead of the whole upper portion of the rocket. Not certain how many of those rockets are left now, but once they run out of RD-180s, there will be no more Atlas 5s, owing to the events that happened back in 2014 with the annexation of Crimea. I wonder if that's a newer piece of music that Tim must have recently put out. So it'll probably be right around T plus 50 or so minutes in the flight. They've actually done. In fact, I'm not sure what. I'd have to see what kind of upper stage that they used for one flight that took it to the moon. And usually, when it comes to uncrewed vehicles heading to the moon, and really when you get right down to it, so do crewed missions to the moon. What they mainly do is essentially raise the orbit by quite a bit, and then make a few course corrections during the course of the voyage to meeting up with the moon. And in the case of most uncrewed vehicles, it just goes into it finds the moon and then just naturally falls into its orbit. They may need to do any kind of powered corrections, but for us, we actually have to use an engine to bring us into orbit. What usually happens is, I believe it's like the third stage, which does the TLI, translunar injection burn. Once it gets about a considerable distance between Earth and the moon, they actually open up they separate the stage with the command service module, which is the command module portion of it, which of course has the crew in it, and then the service module, to which the command module is attached, together called the command service module, will separate, turn around, and some pedals in the stage that contains the lunar excursion model, or LEM, sometimes just LM for a lunar module. They turn around and then they dock with the LEM and stay that way until they get to the moon. At which point, when they get to the moon, they will fire the engine on the service module portion of the command service module to bring it into orbit. Otherwise, they'd be going right into space, going into interplanetary space. And then once in orbit around the moon, they have the crew that's going down to the moon, which is 2 people. Had the USSR gone up there, they would have had 3 cosmonauts and 1 cosmonaut going in the vehicle that's going down to the moon. And from what I understand, they don't actually go inside the module from their command module, or what's the equivalent of it, which is actually 3 modules. The orbital module, which is where they sit in for most of the mission. The descent module, which is below the orbital module, and below that is the service module, which has the solar panels as well as several engines for correcting the doing any kind of adjustments on orbit. And what happens is, what they do is, on the way to the moon, they'll do much of the same motions that I mentioned earlier. The only thing is, I don't know if they actually use a hatch at the top of the orbital module, or if they use the descent module in order for the single cosmonaut that's going to the moon to do an EV to get out of the spacecraft and into the lunar module for going down to the moon. And apparently their module A is smaller and B only has 1 engine, which is used for both descent and ascent. The lunar module that the American program used, made by Grumman, actually has 2 engines, one on the one to bring it to the ground, and then when they leave, they actually leave a lower portion of it that has the descent engine on it, taking off using the ascent engine. So we probably have another half an hour, but roughly half an hour until they actually get ready to deploy the vehicle into orbit. Pardon me, I was grabbing some water. I'm going to step away for a little bit, mainly to get some water, and I might I'll be back in a few minutes. I'll be back soon. So I'll be back soon. Stand by. return. Yeah, it's one of the things I've noticed is that it's taking a bit more effort than I'm normally used to doing when it comes to events like this. Likely due to the stroke back in April. Hope everybody's having a good time zone wherever they are. And basically what they were saying, it was about 93 degrees, I believe, was the inclination, which is the basically the way the orbit goes around the Earth in relation of the equator. It's actually about 3 degrees behind the poles. So it is going retrograde, which is basically going against the rotation of the Earth. Most of the time, whenever you're doing launches from, like say, from whether it's Cape Canaveral, Baikonur Cosmodrome, or in this case Mahia Peninsula, they're launching into the direction of the orbit of Earth. The rotation of Earth. And the idea behind that is, one of the things that happens is that it will also give it a bit of a boost of sorts. It will actually be getting an additional boost from the Earth, which at close to the equator would be a full 1,000 miles an hour extra. So basically, it has to use all of its engine just to get it orbiting. And in this case, it's actually having to use even more because it's going against the rotation of Earth. If it were doing like 180, that would mean it would be going completely against the rotation of Earth. So it would need a lot more powerful, because now it has to overcome the first 1,000 miles an hour. If it's at the equator, you have to a 180 degree orbit would actually have to be. It would have to first, like I said, overcome the first 1,000 miles an hour, and then all that thrust that it needs to go in that particular trajectory to make orbit. That would, of course, it would have to be 17,500 miles an hour, or 27,000 kilometers per hour. Get my ready for bed while waiting. Alrighty, well, good to have you by. Good to have you by. It is one of the few spaceflight ones I've been able to cover directly live. Any of the other ones I've done were mainly just replays. And that's another thing that happened recently was the launch of the second Kuiper satellite, which I would believe is K02, I believe. Or KA02, I believe, is the name of the mission. I'd have to go look it up. Still going to be gone and hanging out in chat. Very good. So we've got probably about 20 more minutes or so until they come to the other side of the Earth. And they're probably somewhere when they pop up, ready to do the circularization burn. That'll happen probably somewhere above the U.S. If I had to guess, probably on the eastern side of the U.S. Sorry, guys. I didn't mean to do all that. That's basically, I'm using a what essentially amounts to a browser within OBS Studio and I'm using a couple of bits of HTML. One to provide a control panel, and the other to actually show the video that's in here. The other way I can do that is by actually putting showing a web browser from within OBS Studio. And that's what I use for X stuff, or the site that originally is known that was originally known as Twitter, which desperately wants to be known as X. And we're seeing that it just come off the we're on the other side of Antarctica, start heading north. And apparently a lot of spy satellites tend to be in polar orbits, which of course have a 90-degree they have a 90-degree orbital they have a 90-degree orbital inclination. That's the word I was after. And I noticed that some of the Starlink orbits that they put in there are right around polar, probably to distribute some of the stuff that go into the various other inclinations, especially the higher one. And the way, in fact, some of the stuff that is in, which is how Starlink works, is a very different version of what we see, for example, Sirius XM, or the old what are called Molnia satellites, for which there is an orbit called Molnia. Basically, they have a constellation of several satellites, and what they'll do is they'll have like 3 satellites. The far side, it's a very, very, very highly elliptical orbit. One will be like, there'll be like 3 of them. One is on one side of the part that's going away from the Earth. One that's coming from the other side that's coming toward Earth, and the other one, which is the side that actually comes closest to it. And actually, no, excuse me. I think those are actually the furthest ones, because when it gets to the apogee, the orbital speeds will be very slow before turning around and heading the other way. And as one is about to come in, the other one starts to fall back toward Earth, and once it gets close to Earth, instead of falling onto Earth, it'll actually make a very sharp hook. And also a lot of these sharp hooks, like I mentioned, to go to the other side, for the other end of the Molnia orbit, work a lot of the way that slingshots work for example, Voyager or various other whether it's between here and the moon or for interplanetary missions. Like I said, uncrewed missions will actually, instead of actually just make a complete dash for it, they'll just make enough of a burn just to put it on track to get pretty close to the moon, basically elevating the orbit. They may take multiple burns. More frequently than not, they will use multiple burns to raise the orbit, and they usually arrive within a matter of a couple of months. In the case of a crewed mission, of course, that can't last that long. That's the reason why they have the powerful engines that get them there very quickly, basically doing all the orbiting, changing the orbiting altitude in just one burn to take us to there. And the only thing you'd probably need to do when taking yourself back to Earth is just enough to break orbit. And if you didn't do what they did over with Apollo 13, they used what is called a free return, which basically it goes and whips around whips around the moon and then comes back toward Earth. In fact, that's how a lot of the slingshots work anyway. They may need a little bit of additional, it depends on how close and depending on how close they get to it, they will either use very sharp slingshots to take it back to take it back to Earth, for example, or they use very shallow entry angles. What they'll use that for is just to use the gravity as a push to push it on to the next destination, whether it's the next planet, or in the case after Voyager 2 left Neptune, to send it on to interstellar space. And in certain cases, they'll use basically all these this little bit of orbital mechanics to take it to the other places in within the solar system. Sometimes in the case of I think even getting to say even the moon, even the sun for the Parker Solar Probe, they actually had to use multiple orbits around various celestial bodies within our solar system, whether it's Venus, Earth, Mars, or the others. And of course, the Parker Solar Probe is the closest vehicle that we've ever sent to the sun, and it's also the fastest vehicle at over 400,000 miles an hour that humankind has ever put in orbit, has ever flown, and is still flying now. So we're about 10 or 15 minutes to the next milestone, which is once it arrives at or near the apogee of the orbit. They will then fire the Curie engine. It doesn't need a lot of thrust to basically circularize the orbit to make it pretty much equidistant throughout the entire orbit. Whenever you see Starlink launches go, they will, in the past, they will sometimes use a second burn of the second stage engine, and given the amount of energy that thing will put out, they only need like maybe a 1 to 2 second burn just to do circularization. But others, what they'll do is they'll rely on the impulse, the ion thrusters on the Starlink satellites themselves to help circularize the orbits. Okay. And of course, the graphic that they have in there, that truncated cone at the bottom is the kick stage, which with a Curie engine. I'm not sure if it uses one or multiple engines in the center. And then up top, you see the a representation of the satellite on top, which of course will be deployed after that. And then I imagine one of the things they'll do is with the with the third stage, they will then deorbit that, so then it can be properly disposed of, helps not contributing rather to the potential Kessler syndrome. Oh, we're on the. I knew it was going to be on the eastern side of the U.S., but it's actually, I believe, we're on the southern tip of Africa, given what I'm seeing there, based on that map, which I believe is being updated by telemetry. And it looks like it's going to be online, on track to go over Europe. I'd say within the next, I'd say about 20 to 30 minutes would put it over Europe. Well, we're not actually seeing this. This is a graphic of this. This is not actually us looking at Earth. It's a representation of Earth based on orbital data coming from the vehicle. when they come back, and once they get to the designated point on orbit, and that's one of the things they talked about, is they talk about all the various parameters such as altitude, inclination, and it sounds like they put everything pretty close to the inclination. And they said they had the inclination right on the money, and they're within a meter. I don't remember the exact portions of it that they were talking about, but basically they put all the orbital parameters pretty much right where they needed to be. I gotta look at a couple things while we wait for just a moment here. And we're going to be crossing over the bulk of the African northwestern portion of the African continent before too long. Within the next, I'd say about within the next 10 or 15 minutes or so. See where the Sahara Desert is. I think it's in the northeastern portion of the continent. About 10 minutes away. Well, we're about 5 minutes around. I don't know how they actually figure the first orbit or so, because we're coming up on the first 45 minutes of the mission, which is roughly most of the way halfway around the planet. Then once they get to that point, they'll ignite the kick stage in the direction of travel, basically in a way to make it just a little bit faster. So then what it'll do then is it will raise the other side of the orbit such that it's equal to the other side. Like I was trying to say, I may not have completely said it yet. I believe I've said portion of it, but basically crewed vehicles do a different variation of what uncrewed vehicles do. The crewed vehicles do a suborbital flight, so that when they get to the point where everything, once they are able to confirm that on-orbit operations are fine. In fact, some of the shuttle stuff, the stuff they'll say right around the T+37 minute mark, they will actually start doing. They will do they'll do another burn using what is called the OMS module, or the OMS engines. OMS, OMS being orbital maneuvering system, as well as, of course, the thrusters throughout the vehicle. The thrusters, though, are mainly to orient the vehicle, whereas the OMS thrusters are mainly for adjusting the orbit. There's the west coast of Africa. We're about, and it looks like we're going to be hitting, finding ourselves in the vicinity of Europe before, I'd say, within the next 10 or 15 minutes at this point. So what happens is in case there's a problem, they do not do those thrustbacks, and they use what I said earlier was called the free return. They basically let the vehicle go all the way around the planet, depending on operational status of the vehicle, whether they have thrusters available or not. They may make it such that they may make I believe they'll do all the regular re-entry stuff in case they use it. They don't actually use the ohms engines in order to do the next portion of the vehicle flight. So what they have to do is they don't do all the post insertion activities, which includes stuff that happens right around 37 to 45 minute mark of the mission elapsed time to actually circularize the orbit. If they don't circularize the orbit, they will fall back to Earth, and they specifically plan it that way. They even do it with all the various crewed vehicles. In fact, that's exactly how Starship has been launched, mainly for the testing side of things. They haven't gotten to the point of orbiting yet. At this point, they now have to get off the ground somehow now, especially after that whole mess that happened. One thing I keep forgetting is that whenever when I'm in here, whenever I pass my mouse over the YouTube video that I'm playing, you guys actually see that. Yeah. It's now getting ready to go, starting to pass over the western tip of Africa, the western portion of the African continent. Actually, it might not actually get over Europe for this particular orbit. Watching I just turned on just looked at the stream itself just to look at it. It takes them about 2 days once they do the translunar injection burn to get to the point where they get ready to do a retrofire to bring themselves into lunar orbit. One of the things I was also thinking about at one point was that from the point they get, like if they, for example, get on the space shuttle and go to the ISS, for example, they're moving the whole time. They're never stopping. They're moving at 17,000 plus miles an hour. And they only stop when they go when they touch down on the landing strip that they touch down on. And in the case of the lunar orbit, the lunar trips, the only times the people actually go onto the planet, onto the moon, those are the only ones who will actually stop during the mission. And with the, for example, for Apollo 11, that would be Neil Armstrong and Edwin Aldrin. Once they touched down and suited up and went on the moon for their EVA. That's what I should have said earlier. I said EV, I meant to be EVA, extravehicular activity. I've seen the inside of the ISS virtually. Oh, is it on like NASA's website or something similar? Because I know some of these will put they'll do like a virtual reality type thing for some various things. I think they might have even done something similar for Mir when it was up there. Oh, it's that medical. Oh, interesting. I'll have to check that out one of these times. Thank you for the heads up on that. See here. Yeah, unfortunately, my logo is covering the thing that it's now showing T plus 48 minutes 34 seconds. It's a fine application. Now imagine if you're an Apollo 13 astronaut on the way to the moon, and the LOX tanks aboard the service module explode to the point where they have to shut all the power down on the command module to save the batteries for once they get back to Earth. That whole area is that whole thing is just, when they go around the backside of the moon, it is outright cold. That's also one of the fact that when they're facing the sun, they're oftentimes also told to do essentially what amounts to rotating the entire complex as sort of a rotisserie. So then, no one particular portion of the vehicle is facing the sun, because when it leaves Earth orbit, it's going to be exposed to the sun pretty much the entire time for the time it goes from the Earth to the moon. So they have to actually rotate the entire structure to make sure that any one spot doesn't get actually exposed to the sun. I'm not sure if they did the same thing with Skylab. Well, one of the things they had to do with Skylab, because the vehicle got launched in a way that caused one of the solar panels to get detached, and the other one's connections to Skylab to be damaged. They had to put a big foil blanket on one of them to basically to keep the vehicle from getting too much sun on it, and they had to limp on just the one solar panel. Sounds like they're getting ready to.
Hello and welcome back as we head into the final few minutes of our Symphony in the Stars mission. We are preparing to deploy a single satellite to a 650-kilometre circular Earth orbit, and we are only a few moments away from that separation event on the kick stage.
We've otherwise had another nominal Electron launch this evening, lifting off from Launch Complex 1 at 7:08 p.m. local time. Now, after the kick stage was separated to its transfer orbit, we have been in a coast phase around Earth for the last 40 minutes or so. So up next is Curie engine ignition on the kick stage. Let's check in with Mission Control for the last few milestones.
Curie ignition confirmed.
We just fired the Curie motor to put it into
from Mission Control. Successful
circularize the orbit.
And so we heard from our GNC team earlier in the show about how Curie is responsible for our pinpoint payload deployment on orbit within 10 meters of target sometimes, which in the expanse of space is incredible. Now, it's only small. It's no bigger than a coffee mug, like you can see here, but it is massively capable. And we can circularize orbits like we are doing today, but we can also perform orbital plane and inclination changes and leverage it to avoid tricky areas of solar radiation like the Van Allen belt.
It's also responsible for our re-entry missions with our Pioneer spacecraft. We've successfully executed 3 capsule re-entries, touching down once in Utah and twice in South Australia. Today is all about circularization, though. The Curie will burn for just under 2 minutes total, rounding out our orbit to a 650 kilometre perigee and a 650 kilometre apogee. Shortly after the engine shuts down, we'll be ready for payload deployment and the separation system will initiate, delivering our customer satellite to their desired location.
I somehow don't think we're actually getting any video feeds from that, unfortunately, but we'll still get more information from that. They should be ending the Curie burn before too long.
Curie cutoff confirmed.
They just shut the engine off, and
there we go. Everything went smoothly for Curie startup and shutdown, and now we are just moments away from payload deployment for this mission. So let's listen into mission control to hear that final milestone for Electron.
And there's a simulation of the vehicle's travel there. What they'll do is they'll monitor the vehicle's trajectory to make sure it isn't tumbling uncontrollably. Make sure it's on a stable trajectory.
Payload
and once they do
confirmed.
that, they just detach the Curie from the payload. There it goes.
Mission success confirmed with payload deployment complete by the kick stage. That is music to our ears for this Symphony in the Stars mission. Congratulations to our customer for tonight's mission, and all the best with satellite commissioning in the days to come.
To the Electron team, congratulations on launch number 68. It won't be long before we're back on the pad for our next mission with Electron, so keep your eyes on our website and social media for updates on the next launch and any other Rocket Lab news. Otherwise, thanks again for joining us for another Electron launch. Until next time, this is Rocket Lab Mission Control signing off.
All right, let's go ahead and head back to the main chatting page then. I'm going to mute that for a bit. So anyway, there's the now another mode that they could actually use the vehicle in is basically leaving the top stage still attached. They use a different version of that, creating what is called a bus, basically where the vehicle provides power, telemetry, as well as any kind of space to ground communication, as well as, of course, possibly even using that particular part of using any radios on that in order to send its own stuff back to the ground and to whether it's the customer or whoever it is. And so yeah, in this particular case, it was more of a propulsion module. But in some cases, especially some of the I've even heard of some very, very small ride share missions, excuse me. Those will actually sometimes they'll actually use the rest of the actual launch, the adapter that actually brings the payload. They'll leave the final payload on there, and what's left on there will be used as the bus. So, in any event, I'd like to thank you so much for joining me. And in the meantime, what we're going to go ahead and do, and we're going to go find someone else to go and spread the love with over on Twitch. I'm going to go check one other thing real quick before we go too far. Okay. And thank you for coming on by. Ooh, I'm looking at the wrong window here. Thanks for the streaming that. Very neat to watch. Yeah, it's always great to watch the vehicle as they go up. And on top of that, what I really like the most about that is the fact that you could actually see you could actually hear the stuff coming from the vehicle itself, because we've seen more than a few. I've seen more than a few launches, including all the various separations that happen, as well as engine ignitions, but never a regular on-orbit sound. We have inbound. Trash Can Goddess, thank you so much for the raid. We just watched the flight of an Electron rocket deploying a satellite into a little bit of a retrograde orbit from Polar. So yeah, let me give you a real quick shout out real quick here. Try that again. And like it just came back from a chatting stream. Let's see. And there you go. And I hope you had a great stream. And if you have self-care stuff that you need, by all means, go ahead and do so. Let me see if I can show. I'm going to go do the bulk of the launch portion of it that happened. So let me get I'm going to go ahead and look that up real quick, and then we'll play a replay of the launch for the people who just came in. And for those of you who don't know me, my name is Katt Phloxworthy. I am a techie, nerdy cat girl VTuber based out of Sacramento, and I like to do a lot of a variety of games. And of course, as you saw this evening, I like doing lots of space flight and aerospace shows, as well as whenever I can. I also like to do technology stuff. But like I said, if you have any self-care stuff that you need to take care of, like post-stream meals or heading to bed or wherever, by all means do so. Don't let me keep you here, but I'm glad you came here, and thanks for bringing your community to mine. So anyway, let me swing back to the other one. Yeah, we did a tier list ranking of dresses from a dress-up game. I'm gonna have to go check the VOD out. Thank you so much for giving that a bit, friend. Thank you so much. I am also very sleepy. I don't doubt it. Here in California, it's just after 1 in the morning. They actually had a bit of a late start to where they actually started the stream. Started the launch. I originally was doing this. I was originally going to start this they originally started it about let's see. It would have been about about an hour and 15 minutes. It would have been an hour and 15 minutes ago, but we're close to an hour since launch. It's it's 1 a.m. here too. Okay, so you're in the Pacific time zone with me. So anyway, let me see if I can. I need to go look that up real quick here. Okay, I'm gonna go ahead and load up the. We're gonna go to about T-2 minutes and counting, and then we'll show you the launch and all the way up to Seco, where second engine cut off, where they shut down the second stage engine. And you'll see a lot of this stuff, and you're actually going to hear something that I'm not used to hearing, and that is ignition of the second stage engine. So let me go ahead and get this started here. Get this ready here. Oh, excuse me, it's already loaded. All I have to do is reload. I just need to... Okay, I see where it is. Real quick here. Okay, there we go. Okay, hang on a second. It actually gives me minute and second. I thought I'm gonna go. Okay, about ready to start the put us where things start, which is a little bit more than 2 minutes, T-minus 2 minutes before launch. Let me switch over to. Or I need to. Let's see here. There we go. Okay, about to start. Hang on a sec here. We're at the. We're just about ready to go into the terminal count, which is at T-minus 2 minutes and counting. Sorry, I'm blocking the actual the view of the of that particular part, the part that actually has the counter. I'll have to figure that out for next time. I really need a better spot for my logo anyway. This is the Electron rocket, which is much like the Falcon 9 in terms of its configuration. It's a much smaller one. It's about 59 feet in height, and it has 9 engines at the. They're just entered the sequence auto sequence start. Let me turn that real quick here. And it has 9 engines at the base. The first stage. Each engine's about the same, about the size of a tall garbage can. They just stopped putting liquid oxygen into the system. And we're coming up on T-minus 1 minute and counting. They're using a propellant combination of a highly refined form of kerosene and liquid oxygen. T-minus 1 minute and counting.
Anti-gas ring is disabled.
And that white stuff that you see on there is not paint. It's actually frost.
Stage 1 and Stage 2 tanks are pressed for flight.
They pressurized the tanks in advance of launch.
High flow engine purge enabled.
T-minus 30 seconds and counting.
T-minus 20 seconds and counting.
15. 10. 9. 8. 7. 6. 5. 4. 3. 2, 1, ignition, and liftoff of Electron carrying the Symphony and the Stars mission to low Earth orbit at an inclination of 93 degrees, and the vehicle has cleared the tower. The vehicle is now you see the Mahia Peninsula, which is at the southern tip of New Zealand, falling away from us. The vehicle is going to be placing itself above water in the event of an abort scenario. The first event is
Stage 1 propulsion nominal.
The first event will be breaching of the sound barrier at Mach 1.
There goes our Electron rocket with a clean liftoff from LC1, now on its way to space for the 68th time. And we are steadily climbing in speed and altitude as Electron comes up to max Q.
We're about to enter Mach 1 before too long.
It's one of the first milestones the rocket has to pass through to get to low Earth orbit, and we're standing by for it now.
We're at Mach 1. And we're about to enter max Q, or maximum aerodynamic pressure, which is the greatest amount of atmospheric pressure the vehicle will experience as it goes through the lower portions of the Earth's atmosphere. They just call max Q. It has now gone through the highest pressure that it will experience throughout the mission.
And everything is looking nominal across the rocket's speed and altitude. Now that we're past max Q, the next milestones coming up are main engine cutoff on the booster and stage separation. So very soon we can expect to see all 9 Rutherford engines on the first stage power down and shut off in preparation for what comes next.
About a minute or so left in the burn.
Just a couple of seconds after MECO, the first and second stages will separate to lose the dead weight of the first stage. And then the second stage Rutherford engine will ignite and power up to propel the second stage onward to orbit. And those events are now coming up very shortly.
And this gets us to about roughly half, much of the way up toward space.
Propulsion holding nominal. Stand by for MECO in approximately 30 seconds.
We've got about half a minute away from main engine cutoff or MECO. Right now, we're mainly just going up with some downrange movement.
15 seconds till staging.
They're going to call MECO, main engine cutoff first. Standing by. We can hear the sound of that as well.
MECO confirmed.
We have MECO. There's the stage separation. The engine start, and the second stage has started and is pulled away from the first stage. That is the vacuum optimized Rutherford engine, which, like its sea level version of the Rutherford engine, 9 of which on the first stage, they're all electric. They're using electric pumps as opposed to what are called turbo pumps, where they use a portion of the propellants to spin the turbo pump. There's the vehicle that's part of the
Everything is going
payload.
Great.
They're about
so far with
to
Electron,
separate the
MECO and
payload
stage
fairing halves.
cleared.
They
Next
just
will
had
be
separation of the
when
payload
Electron's
halves.
nose cone separates and falls away. We might not see it at night,
I guess
but
it hasn't
we
yet.
should
There
hear
we
it
go.
called out in mission control, so let's listen in.
Fairing separation confirmed.
Fairing jettison confirmed.
Nicely done. That's fairing separation confirmed across the nets as Electron continues on nominally. We are now at 130 kilometers in altitude and traveling more than 9,000 kilometers an hour. All is on track with the mission, with another 5 or so minutes to go of engine burn time for the second stage.
And throughout this particular portion of the burn, you'll see an item that says battery jettison. Because, like I said, this uses electric motors in order to operate the pumps that delivered propellant into the engine. It needs batteries somewhere. There are a total of 3 of them. 2 of them are on the outside. You're seeing one of them, and the third one's inside the vehicle itself.
The plot lines for our planned and actual trajectory are closely matched on the right-hand side of your screen there, which is exactly what we want to see. And now that we are at T plus 4 minutes, 36 seconds into stage 2 flight, we have got just over 4.5 minutes left of engine burn time before we reach SECO and stage separation.
And notice that the fuel is actually going down faster. They burn the engines rich, mainly so then they can have some cooling. And if there was a turbo pump in there, it would be running a lot more rich because it needs the cooling.
Coming up next for the second stage will be
badly.
battery hot swap for that Rutherford engine. So every one of these engines uses an electric pump-fed cycle for its propulsion, with batteries used to power its electric motor. But the length of the engine burn time on stage 2 means that the battery pack it starts with will run dry before the engine is due for shutdown. So, Electron performs a maneuver called the battery hot swap, and that swaps in a fresh pack of batteries to keep the engine running for full duration. When that happens, you should see the first set of battery packs eject from the second stage and fall away, so let's watch out for that now.
Like I was mentioning earlier, because it's using batteries and to drive the pumps on there, that weight does not go away. You actually have to jettison those batteries in order to get that extra speed, because unlike turbo pumps where you're burning fuel and oxidizer
discharge holding nominal, approaching hot
to reduce weight, in order to reduce the weight, they actually had to physically drop those two batteries alongside the engine. And we're going to see that in just a moment. In fact, that's coming up very soon.
Throttling down.
The battery hot swap event will happen right at about the same time. You see the vehicle itself on the payload itself on the right, standing by for battery hot swap event and jettison of the outer batteries.
Battery jettison.
There goes the batteries.
Excellent call out there, and a clean battery hot swap on the second stage. The Rutherford is continuing to power the mission on past 198 kilometres in altitude at speeds of more than 1,600 kilometres an hour, coming up close to the orbital insertion speed for final stage separation in just a few minutes.
And watch the speed up in the upper right-hand corner. Once it gets close to about 27,000 kilometers an hour, they just saved the
All right, well, that
the flight
glowing
termination
nozzle
system.
you can see on your screen is our Stage 2 engine, our vacuum-optimized Rutherford engine, powering Electron and its payload, now past 201 kilometers in altitude and 19,000 kilometers an hour.
And we're coming close. I'd say we have a little bit of burn left. One time, though, unfortunately, a battery hot swap failed because the internal battery wasn't properly connected, and we saw the engine just flame out. And basically, the engine. I mean, we are just
moments away from the final stage separation between Stage 2 and Electron's kick stage, preceded, of course, by the shutdown of the Rutherford engine for SECO, or second engine cutoff. The Rutherford engine on the second stage will throttle down before shutting off completely to allow for clean separation of the stages.
From there, the kick stage will enter a coasting phase around the Earth before we light it up for payload deployment within the hour. But first, let's listen in for that SECO and stage separation call out from Mission Control.
So at this point, they're getting very close to orbital speed. In fact, they're very close now. So here we go, coming up on SECO. In fact, we can hear that.
SECO confirmed.
SECO has just we just had SECO, and now the entire vehicle is in orbit and is in it is now in a coast phase right now.
Stage separation confirmed.
And that is SECO confirmed by Mission
the
Control,
uppermost
along
stage of that?
with the kick stage also confirmed to have separated into a nominal transfer orbit with its payload. Well done to everyone involved in the mission so far.
Well, from here, we have a bit of a wait until we rejoin the kick stage and its satellite on the opposite side of the planet after its elliptical coast of Earth. Once that happens, the kick stage should be in the prime position to perform a course correction burn that sets its trajectory to a circular orbit for payload deployment.
Excuse me.
Join us again then in about 40 minutes or so to see out the final moments of the mission. See you soon.
Actually, instead, we're going to go straight out. Let's see. Excuse me. Let me try that again. There we go. Plus, I need to mute this so I can hear what I'm doing. And on top of that, get ready to end the rest of the end the stream. Anyway, thank you, folks, again, especially those who came in by way of Trash Can Goddess's raid. Thank you so much for coming in and to watch all the stuff that was going on. Now let's try again. Let's go find someone else we can spread the love to. I'm going to go ahead and stop that real quick here. And I'm going to go check see who we can go say hi to on Twitch. Yeah, unfortunately, and a little bit of background on what they were talking about near the end, where they were basically deploying the second stage, the third stage, which has a small engine on there. They actually showed a picture of it which can fit into your hand, which is called the Curie stage, named after Pierre and Marie Curie, the one of the earliest people who had their who learned a bit more than about radiation they ever cared to learn about. Oh dear. But anyway, the point being is that they made some very important discoveries about electromagnetic ionizing radiation, most notably about radioactivity, along with Röntgen, who discovered X-rays. So anyway, basically that bit of that part actually has a very small engine. Even though it doesn't actually put out a lot of power, it still puts out enough to either augment the orbit in a way of either raising it or lowering it, and apparently has enough power to even change inclination. And the other thing that it does is it also in this particular case, it augments the orbit by making it a circular orbit, because when it normally comes off a launch vehicle like that, it's in an elliptical orbit, basically where it's closer at one side, which is the perigee, and in this case, it was also going toward its furthest point, which is the apogee. At the apogee is when they do when they fire off the Curie engine to what is called circularize the orbit, and what that does is that makes the orbit of the vehicle equidistant throughout the entire orbit of the planet or whatever body it's operating around. Let's see who we might say hi to. And I hope everybody had a great evening. Yeah, basically what happens is after launch, it's about 50 minutes into the flight, and it's on the other side of the planet. Had a great evening. Thank you. Hey Alice, how you doing? Good to see you. I hope you had a great evening. I don't know if you caught the stuff that I showed, which was the Electron launch that deployed a satellite in orbit, and they did a slightly of what is called a retrograde orbit. Basically, most satellites get launched to what are called posigrade orbits. Basically, they launch into the direction that the Earth is moving, so they don't have to use nearly as much fuel. But since they're going slightly against it, they have to take that out of the fuel that they have and burn that much more just to get the actual orbit to work. If it's in this case, it's a 93 degree inclination. If the inclination were 0 degrees at the equator, they would get the full benefit of the Earth's rotation. Whereas if it's doing a 180 degree inclination, that's basically this. It's going along the equator, but if they were doing it at the equator, they'd be that 180 degrees is actually against the rotation of the Earth. They basically have to take the Earth's rotation out of the equation, and they have to burn that amount plus what it takes to do orbital operations. So yeah, it's kind of interesting to figure all that stuff out. So anyway, that costs a lot of fuel. Oh yes, it would definitely. It's, any retrograde rather orbit actually incurs a penalty as far as fuel burns go. If it goes posigrade, which is less than 90 degrees, and anywhere between 270 and 0 degrees, that would be those would be posigrade and wouldn't cost as much. In fact, they actually have to add that into this. They actually take that out of how much you have to burn, whereas the other one they have to add to how much you burn. So yeah, you're absolutely right. If you're doing a retrograde orbit, you actually have to use or retrograde path. You have to actually burn. You have to burn a whole lot more fuel. I thought you can't have a lot of fuel in space because the heavier the fuel is, more fuel that you need. No, I suppose there's a limit. No. Well, actually, here's what happens. As the vehicle is burning its fuel, it's actually getting lighter. That's one of the things they also take into account when they do that. The main thing that is different about the Electron is, unlike, say, most other rockets, such as SpaceX's Falcon 9, ULA's Atlas Centaur, and Vulcan Centaur, and others, they use portion of the propellants in order to actually spin the pump up in order to move propellants from the tank into the combustion chamber. In the case of and basically what happens is that automatically deducts itself from the system, whereas with an electric pump, you still have the batteries to consider, because once they've actually been spent, they're sitting there and they're dead weight. You have to drop it, otherwise it will actually slow it down, which is why they said right around the 2/3 of the burn on the second stage, they actually dropped the two batteries that flank the battery on the Rutherford on the outside, on the upper stage. The upper of those two stages that get Rutherford powered, those have to be dropped out because, first of all, they run out of battery for that particular phase of the flight, and they have one inside the actual rocket itself to power it the rest of the way. They have to get rid of that weight in order to make it to orbit. Yeah, I never thought of that. Yep, it is. They have to take a lot of that stuff. Whenever you hear people talk about lots of money being it costs a lot of money to put things in orbit, they are not kidding. Because there is, even right now, even when they talk about right down to the last kilogram or pound, depending on which unit of measurement that you use, it's very expensive because you're getting them from a dead standstill on the Earth to 17,500 miles an hour or 27,000 kilometers an hour just to go into Earth orbit. I do my damnedest. But anyway, let's see, go ahead and let's see if we can it's somewhere to see where we can say let's see if we can who we can go say hi to. Yeah, that was that's always a lot of things to learn about that, because even driving a car, even when it comes to inertia and stuff like that, you learn when it comes to Newtonian physics, as well as that it applies to just about everything. Like with the rocket launch you saw, the train that you may have taken to go somewhere, or even when you're driving your car. Hell, even my joke for the fact I drive a hybrid is I have three different sources of power: the battery, the gas that's in the engine, and Newton's first law. Newton's first law, of course, is an object in motion will want to stay in motion, or an object at rest will want to stay at rest in case an outside influence actually changes what's going on. So yeah, in the case of electric motors, in the case of electric cars, remove the gasoline, so it only has two different sources of engine power, and of course a regular gasoline will only have one, which of course would just be the engine. Because one of the things they do with hybrid and electric cars is that they take the use they make extensive use of all that motion that the car gets made when the car is moving. They move a lot of that. They take all that motion and actually turn it into power by storing it in the battery. So, and on top of that, if you've ever driven one thing you have to learn when it comes to driving hybrid and likely electric. I've never driven an electric. I just have a hybrid. When you take your foot off the throttle, you don't get the normal engine braking that you would normally have. Instead, it just keeps coasting. Although some of them, if you have like a sport type setting, it'll actually let you coast further. And it won't charge the battery near as quickly. If you use an economy setting, it'll actually charge it faster, but it'll cause your car to slow down faster if it's once it's on the in the charge cycle. Anyway, let's see who we could actually go say hi to. I think I know who we're gonna join today. Hang on a sec here. Let me mute that real quick here, and I'm gonna close the tab here. We're gonna be joining Mika Magica, who is playing Splatoon, presumably Splatoon 3. So in the meantime, let me go ahead and get things set up here. Do pre-raid situation going here. Okay, we're gonna go ahead and check in and see how she's enjoying her evening. But before we go, let me go and give you some raid text real quick here. There is some text for those people who don't have subs, and excuse me. And there's raid text for those who do have subs, and I'm going to grab it myself as well. So in the meantime, I'm going to go ahead and before we start, I would like to say thank you so much for joining me, and thank you so much for enjoying. And I hope you enjoyed some of the blathering I did, talking about Newtonian physics, rocketry, orbital mechanics, all that cool stuff, as well as of course various things that ultimately deliver a lot of the stuff that we take for granted, such as having all this nice stuff that needs a satellite in orbit to work to do. But in the meantime, we're going to go ahead and start the raid. So in the meantime, I'd like to say thank you so much, and thank you so much for coming in. And as always, I like to say Slavu Ukraini. And until then, until the next time, hopefully it'll be sometime this weekend. I'm going to see what kind of stuff I want to play this weekend. But in the meantime, thank you so much for joining me and watching some of this rocket activity. But in the meantime, and I hope you have a good time in the meantime. And I will see you then. And stay frosty, especially considering it's hot for those of us in the northern hemisphere. And I will see you later. See ya. Bye.